All right, good morning, everyone. Welcome to week 2, and a special welcome to all the people who've come into the course a little late. I know quite a few students have come in over the last few days. So welcome to you, welcome to COMP1521. We deliberately don't put any new material in the first week's tute and lab because we know there are people coming in through week 1. So the week 1 tute and lab are revisions, C revision. Still very worth doing, still very useful. Make sure we're all up on the same page in our knowledge of C. So if you come in late, don't panic. The week 1 tute lab is not due for 6 days. It's due 9 o'clock, 9 p.m., 9 at night next week. So you've still got 6 days to catch up on the week 1 exercises. You've probably come in through COMP1511, so it's exactly the same thing with auto tests and give and exercises. The tute question and the some sample answers are up as well. Hopefully you have an email from me with all of these links a few minutes ago. So please do last week's lab. Well, that applies to absolutely everyone. Please make sure you've done the week 1 lab exercises, submitted them with give. You can submit multiple times with give, of course, and they're up to speed. So everyone's got until Monday of next week. This week's lab exercises also due Monday of next week. So that will be the normal pattern, is the lab exercises will come out and they'll be due 9 o'clock of Monday of the following week. We'll do something different around Flex Week, but that's the normal pattern. You will have noticed in my email there's a link to sample answers for the tutorial. We try to have at least some simple answers you can look at for each tute question. You think you've got a better answer, or you feel free to send it to us and we'll add it and improve the answers. But we post I think it goes up, it's sometime Friday. It's just after the last tutorial on Friday.
I think it's 3 p.m. Friday. Yeah, 4 o'clock.
Dylan thinks 3, I think 4, but you got nothing to do Friday night. COMP1521 tute answers are your friend. All right, where are we otherwise? Well, the 11 o'clock daily 11 o'clock news is getting a little better, but it doesn't look like we'll make it to campus. I was talking to the Associate Dean who was saying, yeah, look, if we can get students to campus by the end of the term, we'll do something for them, but he's not hopeful, I'm not hopeful. You're seeing the same numbers as me, so I'm afraid it may be next year before you're back on campus.
Actually, it's 7 o'clock.
It's 7 o'clock. There we go. All right. Is there any other news? Not really. So this week's lab exercise. Well, this week, yeah, there is. I wanted to talk about this week's lab exercises in particular. We dive into using bit operations in C to pull apart values. It's something we really need to understand for this course. The very bits of doing things with the very bits of a value, the binary digits of a value. So there's a lot of lab exercises this week. There are challenge exercises, and I should warn you, the challenge exercises are very challenging. Well, some of them are. So don't panic if you can't do some of the challenge exercises. I'm not expecting many people in the class to be able to do some of the challenge exercises at all. The other thing would be always, I guess it's okay in week 2, but always trying to make good decisions in your life about, should I be working on my maths assignment, or should I be spending time trying to do the 1521 challenge exercises? So make good decisions there. You don't need, in terms of marks, you don't need to do the challenge exercises. I think we guarantee you 95% without doing the challenge exercises. So if you want to be perfect, you can't stand to drop 0.2 of a mark. Try and do a couple of challenge exercises, but you still don't have to do the really hard ones to get a perfect mark. You just have to do a couple. Probably if you're a very careful sort of person, you're worried you might drop a few marks on the standard exercises. Or miss a few standard exercises. It won't be a few marks. You might do a few challenge exercises just for safety. But in the scheme of things, yeah, as I said, yeah, working on the maths, your maths might be just telling you from experience and talking to lots of computing students that they've done things that it's got them maybe 1.5 extra marks on their comp course, and then they've failed maths or whatever. So please don't be that student. All right, but okay. You're seeing things in this course that are fascinating and you love. Yeah, that's great, and we'll give you plenty more. The labs is Brandon's asking in the chat. I think it's 7 out of 8. If you look at the course outline, there written in blood is what we'll do in the course. So for CSE courses, UNSW courses, I hope generally, we set out how the assessment's going to be at the start of the term, and then we have to follow it. So we sort of set up a contract with you at the start of the term saying we're putting the course down, labs are going to be worth X%, assignments are going to be worth Y%. And we might vary things a tiny bit, but certainly nothing that would disadvantage you or any decisions you've made. So I think it's 7 out of 8, but you can look in the course outline and that's what we'll go with. We're pretty proud in 15121 because we actually put the formulas in one place in the configuration and then try and propagate it everywhere into the marks calculations, into the course outline and so on. We do make mistakes, but we try to have one source of truth that goes everywhere. So if the course outline says 7 out of 8, then the same source is used for the marks calculation. It's a goal at least. All right, let's talk. Justin's asking, is the challenge exercise marking the same as 1.5? Well, it's regular marks, but you'll just finish up with too many regular marks if you do the challenge exercises. So I guess it's bonus in that sense, but the marks for challenge exercises get added to the marks for regular exercises, and if you get more than a certain amount, that's all you need. Yeah, I'm afraid lectures online, I miss chatting with students after lectures in particular and finding out what you're all doing, but tutes and labs for sure next year. Big lectures, I don't know. You can read the public health situation as well as I can. I don't know if we're going to have big lectures in lecture theatres early in the first term next year. We'll certainly have small classes. Everyone expects to be back in tute labs with tutors helping you starting next year. Too many questions on the chat. Are challenge exercises similar to exam style questions? Yeah, the challenge exercises could be the hardest questions on the exam. So if you wanted to show you deserve a HD, I might expect you to do a challenge style exercise on the exam. They're not you don't have to do anything like that, anything near that hard to pass the course. Yes, it would be sad, Brandon, if you went through a 5-year degree without face-to-face lectures, but I don't think that's going to happen. I feel like, I'm sad for people I know a few people, even in my house, who've started uni in the last year or two, and it's not the same. Right. Asher's asking, is there a quick way to copy the lecture code files to my file directory? I'd say come and do COMP1521 with me and I'll show you quick ways to do that, and so many other things. Someone might help Asher in the chat with a solution that will save her until she does COMP1521. All right, I better get talking bitwise operators. There's my pen here. So we've added 6 whole different operators with weird symbols to our knowledge of C, which I'd call and, or, not, exclusive or, caret I guess, and left and right shift. Interesting syntax, and it's a little confusing because and or and not are somewhat similar to the logical operations. Yeah, they're pretty similar to the logical operations, except logical operations, double and operates on a whole value, double or operates on a whole value, and a logical not, an exclamation mark, whole value. It'd be good to experiment with those. Try putting some values into both of these and see if you can come up with where they're the same and where they're different. Experiment. Did I say experiment? Alright, so I've got slides on the screen, but what did I do? We put in the lecture thing a program for you to experiment with, which was bitwise.c. Alright, I'll pretend that everyone in the class who was here last week has got this program and experimented with it, and it uses a second program, printbits, compiled it and experimented with it. And I'll pretend that it's only the people who've joined the class that I'm talking to right now. But get this program, run it, put values in it, and check what happens with bitwise operation. So I'll type in a couple of sort of random values, and it shows you the result here. It's saying if you take this, it's showing you what A, B, and B look like in base 2 binary, what they look like in hexadecimal. And again, I said last week, so I'll repeat that for people who are joining late. If you should be able to do that conversion in your head pretty easily, because every hexadecimal digit is 4 binary digits. So if you can memorize just 16 conversions, which is not that hard, they're all very logical, that you just have to know how to convert a single hexadecimal digit into 4 binary bits, or back the other way, and then you can do that conversion. This conversion to decimal, that's a much harder calculation. We generally wouldn't ask you to do that in your head. I mean, you could if you, but we'd generally do that with a program. If you haven't figured all of this out, that sort of conversion, or you've joined us late, make sure you understand that. It's year 8 maths, and you were a star in year 8 maths, so you won't have any problems with it. Just figure it out. There's excellent online resources for it. You can ask questions in your tute if there's any subtleties that confuse you in your tute this week. All right, noise. Let's go back to my lecture slide. So that program, that program was an opportunity to explore these things. What we wanted really there was to run the program rather than read the program. This is boring C code I'm looking at on the screen for this program. But lets you check these things. Yeah, you can explore that. You've got to think about what odd and even numbers look like in binary to figure out why this works, and also what's true and false in C. And nice little exercise for you. Alright, that was OR. That was the AND, OR, NOT to negate a pattern. Andrew's favourite bitwise operator, exclusive OR, much more fun than the others. The shifts, which we'll make heavily, my life advice is just use unsigned values or unsigned variables if you ever want to shift. If you're, whatever you put on the left hand side of a shift, make sure it's an unsigned value. The easiest way is just put a variable there and make sure it's an unsigned variable. There are, if you really know what you're doing, there are cases where you don't have to do that, but honestly you don't need that hassle in your life yet. Just unsigned variable on the left of a shift and your life will be happier in COMP1521 and perhaps beyond. That's the program in operation. That's what the code looks like. Ooh, alright, so we have another program to look at. Let's look at code here. So I apologize to those of you who sort of read through all these and figured it out. Well, I don't apologize. I'm happy for you, but bear with us while we recap this for people who joined late or people who perhaps didn't have a good week last week. There's the dot. Oh, we used it with, so we've got an extra print bits function which we're using in a few of these programs, which I've put in a separate file because I want to use it in a few of my programs. So I want to use it in bitwise.c and some other ones. That was its header we saw, and this is the guard here, which is a cute way to ensure there are no problems if this file gets included twice, which does happen. Yeah, we'll come back to this. How does... Well, no, we won't come back to this. We'll talk about this in it first. So here, I thought this suddenly, that previous code, not beautiful at all. This is a thing of joy. This is lovely. This is something I'm really happy to be showing you. So this lets me pull out the nth binary digit from a value. It says its argument is an unsigned 64-bit value. The way C works, you can actually pass a 32-bit value, a 16-bit value, or an 8-bit value there, and the code will also work. C will automatically do the type change for you. You can't pass an unsigned 128-bit value, but that's okay. Well, you can pass it, but you'll only see the bottom 64 bits. You'll lose the top 64 bits in the type conversion. How do we get the nth bit from this? We shift the value across. Now you remember my life tip? You're doing a shift, left shift, right shift, just make sure it's unsigned. So what's the type of value? There's a U there, that's unsigned. Good, that's safe. That doesn't mean it's just avoiding one sort of problem. It doesn't mean that there might not be other sort of problems. We bring it across n positions. So the bit we're looking for is now is the last bit, the bottom bit. Yeah, it's very hard. It's now this bit here, you like. Shift it across, so the bit we're after is the least significant bit. Least significant, bottom, bit 0, all ways of describing it. But bring the bit we want across, discarding bits below it. Now we just want to be left with that bit. And this operation I'd call masking. This is the result of AND. AND with any value gives you all the bits that are set in both values. So if I AND with 1, 1 is a binary number, 00000000001. If I AND with that, I'll only be left with whatever the bottom bit is in the other value. If that bit's 0, I'll have 0. If that bit's 1, I'll have 1. I'll be left with only that. So the result of this operation can only be 0 or 1. Saying, shouldn't there be a comment in your code there? Yes, there probably should. That would be a useful assertion there. Saying at this point, bit must contain the value 0 or the value 1. And then I return it. So how do we print the bits in a number? How do we print the bottom how many bits of a number? We start at how many minus 1, go down to 0, and get the bit, print the bit, get the bit, print the bit. So if how many bits is 15, this loop will execute 15. Oh, this loop. Again, people coming in late. If you've come from 1511, maybe you haven't seen for loops. For loops, not much different to while loops. That for loop can be simply written to a while loop. Let me write it to a while loop. A for loop starts with an initialization command, which could just be put in front of the while loop. It has a condition exactly like a while loop, no difference at all between this, and it has a post step, a loop step if you like, which you can put at the end of the while loop. Then that's exactly the same code. Is there any difference? That seems such a trivial difference. For loops we can write more compactly. For loops we can declare the variable within the for loop, which is sort of nice. The only difference that it really arises if you have break and continue. There are subtle differences there. If you can explore that yourself. Alright. So that's another thing you have to get up to speed with. That was another week 1 topic. If you haven't played with for loops, get your old C code with while loops and rewrite it all into for loops and see if it works. Do you have to do that when you write code in this class? No, you can keep writing codes with while loops. It's only not going to play, and you produce a correct program that uses while loops. I'll be smiling, but we will be using for loops in lots of example code, lots of example solutions. So you have to be able to read for loops. And if you go out to internet resources, a lot of them are going to use for loops as well. Why do they do it? If once you're used to reading for loops, a well-written for loop, it's easier and faster to read than a while loop. That's a well-written for loop. Poorly written for loop is yes. Oh, Dylan's saying bit 0 is the least significant or rightmost bit. Yeah, I'd agree with that. But so you generally, if you've got a 32-bit number, you'd say bit 31 was the most significant and bit 0 is the least significant. And I think people pretty much stick to that convention. Yeah, I think that's a pretty good. There won't be an exam. We would never give you an exam question that depended on you knowing, which way the bits were numbered. That would be just stupid. People generally do that. So we'll make anything crystal clear about. You don't have to memorize things like that. And we'll give you an example. Oh, excellent question there from Anshul. Are there any benefits to using for loops compared to while loops in terms of execution speed? So will my code run now? I've rewritten that for loop as a while loop. Will it run slower? Answer, no. If in general compilers go to so much work, particularly C compilers, to produce the fastest code possible, so that those two loops will, if they mean exactly the same thing, and they do in this case, they will produce exactly the same code. So compilers are smart. General, what we aim to do is to write the thing that is most obviously correct. Now, when you get into things like writing device drivers, there can be subtleties, and then you really, if you know how C programs are implemented at the machine level, sometimes you have to do things, rearrange your code in something like a device driver to get a little bit more speed, a few nanoseconds more speed. But yeah, that's a good Girachan's. Yeah, it's an interesting point. He's saying easier to get an infinite loop with a while loop. It's easier I think, yeah, I agree that it's easier to write a wrong while loop perhaps. In a for loop, you're sort of setting out things a bit more. You're saying initialize, condition, step. And it's perhaps a little clearer, but it's not a huge thing. By the way, with us today we have Dylan. Jashank's disk had died and Zach had problems at his house. But Dylan has managed to somehow join us from northern New South Wales. And
I think the main two reasons to use a for loop. First off, there are slight differences with variable scope, which is an interesting topic. But the main thing, the reason I would use for loops is because it puts all of the important information about the loop in the same place. You can see the initialization, the condition, and the step together. You don't have to look down to the bottom of your body of your loop to look for the step. It kind of just puts all the important information in one place. But then there's slight differences, as Andrew said, with how break and continue work, and also with the scope of variables.
And to repeat, by the way, maybe you're getting better at C programming, but maybe all programmers, but certainly programmers in their first year of programming, 2 years of programming, overuse continue. They just get into trouble with continue. Continue should be used sparingly. There are patterns that, yeah, it's true, there are nice patterns with continue, but there's lots of bad code with continues as well. Break is less problematic, and they both work a bit more. Both work a bit better, more logically, not logically, more usefully with for loops. But what Dylan's saying is this what I've circled there on the screen is setting out the iteration, what the loop does, and that's a crucial thing we're interested in if we're trying to understand this program. Is how many times does the loop execute, over what values of I does the loop execute it. So it's all set there on one line. You're saying, but what if the loop changes I? Yeah, it's better if you try to avoid that sort of thing. The other thing is for loops is this iteration doesn't have to be just a simple counting. It could be down a linked list. It could be any number of things. So we like for loops for that. It does take some getting used to the syntax, and I guess C doesn't let you really abstract the iteration. So well, it's more difficult in C than other languages. Yeah, Python iteration is much more abstracted. You can be much more a general concept. But it's important in CLS at least to get it this far to say this is what I'm looping, and then this is what I'm doing each time around the loop. Max says, I heard there is something called goto. Yes, we will show you goto later in the course. It's a joy to see. It's something I'll talk about that then, but it makes break and continue look positively friendly in terms of its effect on the readability of your code. And Carl, I'm not sure, Carmads is asking, we need to understand binary and base 16. What are good resources to link for that? We've linked some stuff to the class web page. I think we've linked in Wikipedia. Wikipedia is superb for these sort of things, formats of floating point numbers, representation of integers, bases, things like that. We've linked those. We've linked some old videos for the course, I think, as well. And so, class web page, check it out. And yeah, but please make sure you're really on top of binary and base 16. Alright, that was printing the bits of a number. What else? Oh, sorry, we're still recapping. God. Here's my code to calculate 2 to the power of n. This would be an interesting one in terms of speed. Is it slower or faster than doing this via multiplications? So I want to calculate, say, 2 to the power of 15. On screen, I've got code to do that. And that's actually what really happens in the silicon, is something like this. So that was shift as multiply. And it's also bringing in print bits, I think. Yes, it is. And we'll call it shift, or SM, there we go, for shift as multiply. Let's run that and say, when it's taking a command line argument there and converting it. So we'll say 2 to the 15th, which should be 32,768. And it is 32,768. Alright. Would that be faster than doing a multiply, doing that with a multiplies? It might be. C compilers are so multiplies are quite an expensive operation compared to something like addition, and the bitwise operations are even faster than addition. Multiply in the CPU, we can't cover how you implement that in silicon in this course, sorry. But multiply is actually done by a pile of shifts in the CPU. So a single shift is much faster than generally the multiply. But compilers are pretty smart, so they might see times 2 and think, I can turn that into a shift if that's safe. Anyway, the important thing to see is shifting a bit position, shifting your bits of your number left is the same as multiplying by 2. So if I take 1 and shift its positions 3 left, that's the same as going 1 times 2 times 2 times 2, or 2 to the 3. It's just, is this useful programming? Sort of. It's nice to understand this stuff. So it's just showing you something. Let's run it once more. If you're trying to do calculations in your head and match things up, an incredibly useful thing to remember is that 2 to the 10 is the same as 10 to the 3. You're saying they're not quite the same, Andrew. It's 1024. If you're doing rough calculations, that doesn't matter. In physicist terms, that's a perfect match. A physicist would be, I think that's showing you something about the universe, probably, that they're so close together. Well, actually, it's actually really useful. I really like students to have done physics. The way physicists think about things, it's enormously useful for understanding so many problems. They just try to grasp the big bones of a problem and think about it that way. And it's a great way to come to terms with something before you do more precise sort of calculations. All right. not hating on physicists here. Physicists are great the way they do things. We have an excellent, by the way, excellent physics courses here as well at UNSW. Most of you take physics because you have to, so I guess I don't have to advertise them, but the physics teaching at UNSW is superb. Alright, what am I trying to do? Oh, alright, now I'm trying to get to getting the bits out of a value, and that's what this week's lab is about, is pulling apart or constructing values. So saying, I want to get these bits out of that value and figure out what they mean, or I want to put these bits into this value and get it. So this is a way to doing this. This is my first step. I want to construct I want to, given a value, say 7, in a 7, I want to construct a value that is 7 ones, and that's it. And this is done in a great way. What I do is I start off with a 1, I send it across 7 positions, so I've got a 1 followed by 7 zeros. You're saying, that's not what you want, Andrew. But then look at my next step here. I subtract 1 from it, and think about you go back to year 4 and your subtraction. How do you do that? You subtract 1 from that, you'll come back to 0, 0, 0, 1, 1, 1, 1, 1, 1. Isn't that lovely? I think it's not super complex, but it's beautiful. I want 7 ones, so I send a 1 across 7 position to have a 1 followed by 7 zeros. Subtract 1, and I'm down to 7 ones, and it works. Andrew's got a question. What does assert do? That's an excellent question, because I don't know if assert gets a lot of mentioning in the course COMP1521. So let me first show you my lovely, I just got to remember what this file is called. Let me clear my scribbles off the screen. It's called set low bits, of course it is. Compiler, bring in my print bits function for the SL. Just demonstrate it works. Give me a number with 30 ones. There we go. That's the number that's made up of 30 ones. Isn't that beautiful? Assert. There on screen is assert. What does assert do? Well, we can work out where it comes. Oh, it's interesting. Why has that got double quotes on it? I would say angle brackets on assert. Don't know how that happened. There's a assert is part of the standard C library. What does it do? Almost nothing, actually. If your program is correct and running correctly, assert does nothing at all. What does assert do? If it's given something that is true, assert does nothing. If assert is given something that is false, it normally stops program execution with a runtime error. So it gives you a way to say stop with an error if this is not true. So if n is less than 0 or n is greater than n bits, this program will stop here and not go further. You think, I know how to do that, Andrew. I could have used an if statement and a printf and exit or a return, because this is main. Yes, you could. So this is the same as saying if this is not true, exit. Stop the program and print a message saying something wrong here. It gives you error checking. So it gives you error checking. Why is that good? It's good for a couple of reasons. Let me give you 2 big reasons. It makes debugging easier. The earlier error is detected, the easier it is to debug. So if you're told about the error down here, then you've got to inspect all the code up here until you get to the bug. You've got to work backwards through your code. Alright, so this is a pretty tiny program, but just bear with me for a second. Ooh. This is a pretty tiny program, but in a complex program, this could be a huge difference in your debugging. For things to have stopped here, and it could reduce your bugging time from an hour to 2 minutes. So we want to know about errors early. That's one reason assert is great. The other thing is, maybe what happens down here is dangerous. Maybe it removes files, maybe it makes permanent changes to the world, maybe it gives us the value of how big to make the the girders for the bridge. I don't know how long the wings are on the aircraft we're designing. So assert's good for that. It stops us going on to do erroneous things. But there's more. Actually, and it's probably the best thing about assert is it's telling me, if I'm reading the program, something that must be true. So I'm going in here and I'm trying to figure out this bit of code. I'm thinking, oh well, what does that do? It gives me something it gives me information that must be true. So it's documentation. It's a comment. So it's this really nice. It gives me both error checking, helps my debugging, and it gives me a comment for when I'm reading the program. Asserts are a great sort of source of comments. We use them for things that we don't expect to happen normally. If it's something that would happen in normal execution for regular users, we'd have to put some code there that says if this is true, tell the user what they have to do, what they did wrong, and so on. So it's not a substitute for a proper user interface, though it's certainly better than nothing. Yeah, so this is what you have to do if you want a comprehensible message to the user. If you've not got two arguments, do this. I guess, yeah, it's a good comparison, isn't it? That's an assert, and that's full of checking, doing almost the same thing, but we print out a nice message, and then we stop the program. That's assert. Now, Dylan's reminded me, if you're concerned about super fast code, assert has another property. There is a way, if you tell the compiler produced incredibly fast code, there's a -O flag. If you tell it your priority is speed, 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 I don't care anything about speed, it actually turns off this checking, and it has zero impact. So there's a way you can do all your standard sort of testing with the asserts turned on, but if it's absolutely vital you have as much speed as possible, you can remove any overhead from that. Oh, Ariane is redesigning assert for us. Yeah, that's, I'm probably on board with that. Yeah. And see, yeah, I was asking, why does mask equal 1 mean 32 bits in a row? Yeah, well, you can't tell from that. But where is mask declared? Track back, track back, track back. There, uint32. That's why there are 32 bits in mask. So, if you came in late, yeah, look back through the slides. But we went through a whole pile of numeric type. We removed the whole. We removed a whole pile of numeric type. Sorry, removed. Breathe, Andrew. We introduced a set of new numeric types, and they include some. They're covered in this week's tutorial. I'll leave it there. But this one has 32 bits and it's unsigned. But ask your tutor. They're covered at the start of next week's tutorial. And there's a question: should I leave asserts in my assignment? Oh yes, definitely. So that's the great thing about asserts. They can stay in your code for you to read. If there was some reason we needed to run your code 3% faster for the assignment, we could turn off assert. We could compile it in such a way as this checking was removed, and that tiny overhead, absolutely insignificant overhead, was removed. There are circumstances where an assert can produce faster code, because compilers do a sort of mechanical reasoning about a code, and one thing compilers definitely track is the possible range a value can have. So when they'll do powerful analysis, and I'll try to work out, for this variable here, what possible values it has. So an assert like this then tells the compiler that after this assert, n is in that range. So you can actually get faster code with assert sometimes, which is a little weird. All right. We should keep moving. I'm enjoying this too much and not covering enough. Set bit range. Oh, all right. So I took this and went further to give me something that let me set the particular bits of a number. So rather than just set the low bits, I worked out how to set bitrange.c. And what? I called it SL. Call it SBR. There we go. And I can say SBR. What can I say? I can say set bits from 5 to 10 of the number. There we go. Look at that. So bits starting from 5 to 10 of the numbers set like that. And that apparently is, if you interpret it in decimal, it's 2016. Or I can set bits 0 to 4 of the number. Oh, beautiful. Or let's try it out. Let's set bits 16 to 31, the top bits of the number. We've come in with 3 asserts. That's a nice use of assert there. We're saying the user's given me a high bit and a low bit, and I'll assert that the high bit is greater than or equal to the low bit. I'll assert the low bit's greater than or equal to 0, and I'll assert the high bit is less than the number of bits we've got. All of those things should be true. The code to do it that's just the code we had in our previous program, and now we just shift it across. So step through all of that in your head, make sure you understand this, but that's not so hard. So we want 5 ones. We construct 5 ones the way we did before, then bring it across 5 positions. How would you want to know more about this? Get this code here, the debugging code, and put it there, then copy it there, then copy it there, and copy it there, and run that code, printing out the bits after each operation, and make sure it makes sense. So I said last week, and I'll say it again. I'm not ashamed to say it again. The mark of students who get through this course understand a lot is students who grab programs like this and say, I got to understand this, and they modify them, add to them. They think, oh, I can do this, or what happens if I subtract 2 there? And they try to make sure they understand the program. They get the program, they compile it, they run it, they change it, they think about it. There's a weird bit of trivia here. Oh, that was the previous program. I'll show it. This is just a side note. So I stuffed up here. When I was writing this program, I put double quotes there. You normally put angle brackets for the includes for the C library. I put double quotes, which is normally your own include files. Little known secret. If double quotes will also look for system includes as well. So it looks to see if you've got a include file called assert.h, and then goes and looks for an assistant one. So that's obvious. And we can see that's confusing. There's someone in the chat saying, "What? Has Andrew got his own assert.h?" It's confusing. So we always use angle brackets for system one, so it's clear that it's a system one and not one I've defined. And we always use double quotes for our own one. So I was bad there. I'll fix that after the lecture, or maybe Dylan will fix it while it's all happening. All right, but wait, there's more. What about I want to extract a particular bits of a number? This is what I've got code to do now. Let me show you an operation, then I'll show you how it all works. So this one is called extract bit range. Now we're getting serious. And we're building on those previous examples. Extract bit range, and we'll call it extract. How about that? Actually, we'll go with extract bit. Well, we'll go the whole way. All right, extract bit range. We'll try it out. I've got to remind myself, it takes 3 numbers. Alright, there we go. Suggested example there in the header is, say, give me bits 4 to 7 of the value 42. Did it work? I think it has. It's a bit confusing. Let's try a different. So let's try ask for bits for 7, so something with more bits in them. How about we'll give it that. Ooh. How did that work? Alright. You're saying you typed a word there, Andrew. I put a little 0x in front of it, and this is more so you'll understand lab exercise than anything else. We're using strudel here to take the string. So we've got on the command line we get words which we get strings. There are the 3 there. We use strudel to convert them to numbers. So I've used strudel to convert this to an unsigned 32-bit number. Strudel lets you specify as its 3rd argument the base. But wait, there's more. You could put 10, 16, 8, anything you like there, really. If you put 0, strudel tries to be clever, and it tries to figure out if it's decimal, that's its default, octal, if it starts with a 0, or hexadecimal, if it starts with a 0x. So for the lab exercises, where it's actually quite nice if you can specify inputs as hexadecimal, it's convenient. We use strudel. Strudel is good as well. Strudel gives you error checking. You can use this second parameter for error checking, which I'm not. Bad, Andrew. I probably should, but it makes this too messy if I do that error checking. It's not so significant with this anyway. But if you really want to know, have I been given a valid number, you can use that value there to figure that out. Okay, alright. Oh, sorry, I've accidentally typed in the wrong window. And again. There we go. How did all of this work? Well, did it work? Alright. Is this, where are these 110 here, is it bits 4 to 7? Yes, it is. So I've asked for bits 4 to 7 and it's pulled out the right bits. Let's try a few more examples. Let's pull out then bits 25 to 30 of that number, which should all be zeros. Alright, let's pull out the bottom bits of that number. Let's say pull out bits 0 to 7, the bottom byte of that number. Oh, so who knows what half a byte is called? Who knows what 4 bits is called? It's great, actually. Well, Dylan, do you know what 4 bits is called?
It's called a nibble.
It's called a nibble. I can't actually remember why. You can Google that and then discover. But so we can pull out the bottom nibble. And good news, I think it's spelled. Yeah, how is nibble spelled? Yeah, maybe it's spelled like the rabbit nibbles. But yes, if I was Mark Chi, I'd have a lovely meme with a rabbit nibbling, wouldn't I? Disappointing. In this week's lab, you actually get to do quite a bit with nibbles. Nibbles, decimal digits stored in nibbles or BCD. There are some variant spellings in the chat, which I'm not at all sure about. Alright, but there's the bottom nibble. We can even get the second nibble with this. Oops, that's not the second nibble, that's only 3 bits. So it's a sort of it's a multi-part operation. First, I discover the mask. What do I mean mask? When I want to extract certain bits from a number, if I can construct a value which has got a 1 everywhere there's a bit I want to extract and a 0 everywhere else, that's a mask. If you like this, if I go back in time, back in time to this. This was actually a really simple and trivial mask. I just wanted the bottom bit of that value, so I ended with 1. But that 1 is a mask, the simplest possible mask, just to give me the bottom bit. So this gives me a way of extracting setting up a more complicated mask. So this sets me up the mask to match the bit range I'm trying to extract. Then I do the extraction here by ANDing with the mask, but then I want the extracted bits to be shifted across, so I just have the extracted bits, so then I shift them across. So that gives me the extracted bits. Oh, someone's saying feed. That's weird. What does feed mean as a number? Hexadecimal, base 16. What are the digits? 0 to 9, A, B, C, D, E, F. Yeah, it's a bit silly, isn't it? All right. Let me put a different. I could have written 65261 there and got the same thing. So 0x feed is 65,261 base 10. All right. Now, what now? We're almost time to take a break. Let me see where we are. Yeah, I'll just see it. So, what I want to do here, we'll look at this example, and then we'll take a break. So, what am I trying to do? I'm looking at this. I want to get an integer and print it out in hexadecimal. I've got code, so I'm not going to write code for you, but think about how would you do this? You're saying, I know how to do that, Andrew. Printf has a %x. I just go %f %x. Yeah, all right. How would you do that without using printf %x? The X key in your keyboard is broken, say. How would you print out a number in hexadecimal? Let me show you the program in execution. So we run it. Oh, it's reading from. I don't know why it's scanfing rather than using its arguments, but we're all good with that now. We're competent C programmers. We can say, take your input from as a command line argument. We can do that. Read your number in from standard input. You can do that. That doesn't look good at all. I'm a little bit worried about that. My code is broken. Oh. Alright, let's look at my code. We might take a break and you can debug my code while we break. So it's not doing what it's supposed to. It seems like the digits are backwards. 42 in hexadecimal should be 2a. 2 times 16 plus 10. A is 10. Let's have a look at my code. So that's what we're trying to do. That's my print hex function. So this function, print n in hexadecimal. Way to go, Andrew. Well, that's not too bad. What does it do? Works out how many hexadecimal digits it's got to print. What does size of give me? Size of gives you the size of the type in bytes. So I could have said, well, that's always 4 bytes. So I could have hard-coded 4 in my program. It's a little better, actually. I've said size of this type. So if I change that uint 32, that will change as well. So that's 4 bytes. 4 times 2 is 8. So it'll be 8 hex digits. So here we have something that writes out the hex digits from left to right. So what we talked about, how a for loop nicely encapsulates what the loop's doing in the first line, and then you can dive top down. Whereas a while loop, there's crucial information down here. If we're a good programmer, this is all we need to know about the loop, and we don't muck with which digit further down. The code then works out how to pull out the digit, works out the bit shift we've got to use, masks off the correct bits. And this bit, it's got a real scary bit here. This really could have done with an assert here, couldn't it? Let me show you what an assert here should look like. At this point, hex digit should be greater than or equal to 0. Oh. It's hex digit, yep. And hex digit should be less than or equal to 16. So we should have a value between 0 to 15 inclusive at this point. So that's a nice use of an assert, showing what must be true. If I've got a number...
strictly less than on the second one.
Oh, it's true. Poor programming, Andrew. Thank you, Dylan. So I've got a value 0 to 15. How do I turn an integer 0 to 15 into the corresponding ASCII code for that number? Now you're saying, Andrew, I know. We did this in COMP1521. If you get the ASCII code for 0, what do single quotes do? They give you the ASCII code for a value. So I can get the ASCII code for 0 and add the hex digit to it. That will work. Sure, that works sometimes. If the hex digit is 3, the ASCII code for 0 plus 3 will give me the ASCII code for a 3. Works great for the first 10 digits. Sadly, it breaks here because the ASCII code for capital A is not one more than the ASCII code for 9. Now, if they'd been thinking when they designed ASCII, maybe they could have made it that way. But no, if you check it out, what the ASCII code for capital A, I can't remember any of them honestly. I don't have to, because I can just put a little single quote here and a little single quote here in my C program, and I get the ASCII code. So that trick
the issue is that they wanted the lowercase and uppercase letters to be a very uniform distance away from each other for easy conversion, which is why they stuck numbers and a couple of symbols in between, which is why they're not immediately following each other.
No, I don't think they were thinking well enough about my programming needs when they did that way back in the 1950s. All right, so Dylan's researched, well, maybe Dylan already knew. It wouldn't surprise me if Dylan actually already knew that, but that's what the ASCII designers were thinking way back when they did the American Standard for Information Interchange back in the 1950s. But they can't stop me. I've got a different scheme. So if I've got an integer range, so I've got a range of small integers, and I want to transform them, map them, is what my maths lecturers would say. Maybe your maths lecturers say the same thing. Map them. A function transforming a small integer to another value. A great programming technique is to put the values I want to change to in an array, use my small integer as an index to look up the array to get the value I want. So what I want to do, given 0 to 15, I wanted to go to the ASCII codes for the characters 0 to 9 and A, B, C, D, E, F. So I'll put the ASCII codes in an array and then look it up. But C has a great shorthand for put these ASCII codes in an array. That's double quotes. Single quotes means give me the ASCII code as an int. Double quotes means get the ASCII codes for these characters, put them all in an array for me, Well, it means one more thing, and it then means put a 0 terminator on the end of the array. So that double quotes actually means a 17 element array. Doesn't matter for my purposes because I'll never look at the 17th element. 17 element array, and I've said this is 0 to 16. All right, you'll get your break soon, but you have to listen to another one of my life tips first. Your life will be happier if every time you index an array, you ask yourself, how do I know that index is valid? I work backwards and I see here the assert that says this is a value 0 to 15. I look at the size of this array, it's 17, so I'm good. Always ask yourself that question. If you can't answer that question, something has to be done. It may be adding extra code, it may be you found a bug, but if you can't answer the question, how do I know this index is valid? You've got to do something. Right. That does my transformation. I like that. That's a nice. It's a powerful programming technique that appears in many places. I've got a transformation. I want to do it quickly, but I won't need to transform a small integer to another value. It can be any other value. I put the value I want to do the transformation to in an array, index the array. It can happen in picoseconds. Well, that's not true because it may involve memory. We can tap on really fast. Then I print it out. Alright, I've promised you a break. So there's a bug in this code. I'll leave you to fix the bug in the code while I stand up, walk around and take a break, and I encourage you to do so too. So I'm going to stop talking for 5 minutes. I might put my frog back up on the screen, one of my better frog photos, and we'll take a short break. So back in 5 minutes. All right, everyone, welcome back. I hope you took advantage to get up, stretch, focus your eyes to infinity, that sort of thing. I hope you enjoyed that's one of my favourite frog pictures I've ever taken. No, not John, not a snake. Though I have a lovely snake picture from the same night. I might put that up next lecture, maybe. So, I hope you, in the break, figured out this beautiful code. Now, there's a moral tale with my code. We've seen it's got a bug in it. It's printing out the wrong thing. There's a classic thing with coding where people this often arises where you're doing sort of graphics, and you've got to decide what your coordinates are, and people get confused about what their coordinates is. This 0 and going this way, bottom left corner, or what are your coordinates? Where are you numbering from? And you'll see people who are really good coders will actually do little ASCII diagrams to make it super clear what the coordinate system is, because it's a classic sort of bug is someone gets confused in their heads and thinks 0, 0 is up here or down there. It's a completely arbitrary choice, of course, but how you're numbering things, and that's how I got confused.
You get graphic designers who think it's in the middle, and then suddenly you have icons spinning in circles.
I haven't thought of that, but yeah, all right. So I guess you could have 0, 0 in the middle of the page. This could be 0, 0. That's sort of the way a mathematician would code. All right. So what have I done? Well, I'm writing out hexadecimal numbers. There's a question of which I've got which digit numbering my digits, but I've got confused in my head writing this code. As I said, that's a lesson to all of us to think more clearly about this. I've thought that my numbering system is going n-1 to 0 here, I think. But that's what this code thinks. It thinks the digits are numbered from n-1 down. So these digits would be number 7, 6, 5, 4 down to 0. But this bit of code says the hex digits are numbered 7, 6, 5 down to 0. But this bit of code thinks the digits are numbered 0 to 7. So, yeah, it's only a few lines apart in my code, but I've got confused. So it would be better if I had some comment there making it clear. I must admit I'm not the world's best commenter. Something like this, I guess. You'll often see comments and think like this and think, well, that's obvious. I didn't need to say that. But then you see code like this is broken. So I think if I make this like this, suddenly my code works. If I've got that right. I haven't checked in the chat. Oh. Implicit. Implicit defection. So I have to grab a cert. This time for sure. Come on. Ah, correct result. 42 is indeed that. Let's enter a bigger number. Let's enter 5, 6, 7, 8. I think that's okay. There we go. A bigger number in hexadecimal. Lovely. So there's a lesson to us all. Be very clear. You see this a lot in exams. Students panic. Okay, maybe you don't need to do comments, but even they don't choose good variable names, and then they get confused in their own head. Their code here thinks this variable is used one way, and the code here thinks this variable is used another way, and unhappiness results. So we have to. programming's all about communication, what we want the program to do to the C compiler, but it's also about communication to other people about what this code does. But there's also a communication to ourselves and maintaining a consistent model in our own heads, which is enhanced if we write beautiful code. Someone's asking this one. Shifted value and 0xf. So f, hexadecimal 15. What does it look like in binary? It's 8 plus 4 plus 2 plus 1. So that's 1, 1, 1. So f in binary is that. So everything else will be zeros. So that's a way to get the bottom 4 bits of a number. So this says give me, oh, there's my comment there. Yeah, another way to think of it is it's getting whatever this number is and zeroing everything but all the 4 bits. It's just chopping away all the remaining 4 bits. Alright, that was nice. Dylan, are there any questions I should answer at this point?
I don't think so. Just a lot of people talking about your frog on the break.
And
of course, Max was nice enough to post the daily COVID numbers, which is 1,022 new cases.
But has Max posted the number of testing, which is the crucial thing there?
He did. 82.5% first dose, 53.
That's vaccination, which is
dose.
Nice. But the crucial thing is how many tests. How many tests were those from? We are numerically inclined in this course.
I believe it's somewhere. Where are we? Total tests. Tests in the last 24 hours, 121,000.
Oh, that's nice. All right. Below 1% then. All right. What's this one? What am I doing here? I want to convert. It's not much different to the last one. But it's a nice bit of coding. The bit operations are going to be almost identical, but the coding was different. So let's show you into hex string. It's actually pretty. Why am I doing this? All right, there's a big thing in coding. People, you start working with a new sort of thing, a Pokemon, for example. You're working with a Pokemon representation in your 1511 assignment. You're starting working with a new sort of object. You have to debug. You have to output. So you write code that prints out to standard output, or maybe prints out to a stream, a representation of the thing. A better thing to do, and programmers eventually realize this, is instead write a function that converts the thing to a string. And then if you want to print that out, dead easy. If puts or whatever, printf %s. If you've got a string representing a thing, you can dump it to output. But you can also do other things. You can combine it with other strings. Converting something to a string is a more useful, more powerful thing. Alright, in C, it's a little painful because it involves some mallocs and things like this. So it's a bit of extra work in C. Usually still worth it. In other languages like Python, it's dead easy. And you should write the utility function, convert my thing, my new type, if you like, to a string, and then if you want to print it out, go from there. Alright, so let's show you, if I've got an integer and I want to turn it into a string, let's show you how I do that. It's going to look pretty much the same from, I thought I fixed that message in DCC. Anyway. Into hex string, enter a positive integer, 42. Alright, that looks pretty much the same. What's happening behind the scenes here? What did I want to show you? So I wanted, I did want to show you this. This is good. This is better. I want to produce an array containing a string. How do I do it? I say to malloc, give me enough bytes to hold whatever's going in the string, which is the number of hex digits plus 1 for the terminating 0. Then this code, this is just the same as the last example. Nothing's changed there. Everything the same. this bit's new. Rather than printing out the digit, we tuck it in the right place in the array. So we put it in the right place in the array. Then, oh yeah, there is a slight transformation there. I'll make these consistent, but it's not important. Then we terminate the array. We put the special value 0 to mark the end of the string. So that's sort of the smarter move. If I rather writing this code, this function is so much more useful. Writing a function that gives me back the string. I give it a number and it gives me back a hex string for the number. How would you do this? So the previous example we could have done with printf. What do you do? What do you do if you want to printf? Printf's great. The interface, it's so convenient. But what if I don't want to put the characters to output? What do I do if I want them in a string? Is there a way to do that? Yes, there is. And that's called snprintf. Not the catchiest name. Snprintf. We might change this code to use snprintf. There's one thing I wanted to show you here. This code, you might say this is bad. It's not checking something here. And I'll talk about this much more as we go on. It's not checking whether malloc worked. We're asking for more memory, and it's not checking whether it succeeded or not. You always should check. Now, for complicated reasons, asking for more memory almost always works, at least if you're on a Linux system. There are other circumstances where it might fail. On little embedded systems and things like this. If you're on a general purpose system and you're not running with user limits, on our CSE servers actually you probably might be running with user limits, so I guess it might fail there. For complicated reasons, these requests don't fail very much. So you're thinking I'm requesting 20 bytes of memory, it's never ever going to fail. A nice thing to do then would be put an assert there to say, yeah, the malloc returns a null pointer if it can't give you the memory. You're going to say that's just never going to fail. So you'll see that a bit in code in labs and things like that. That's saying this is going to be not equal to null. That's never going to happen. It's a nice assertion. And if there's something weird happening, everything will stop here. And I can work backwards and work out, oops, this is a billion, not 3 or whatever. That's a nice check. But notice if I've got this routine to turn that into a string, now if I wanted to, then I just want to print, look all I do, %s, print the array, away I go. So if I want a string, I've got a string. If I want to print, it's easy to go if you've got a string to print it. This is a much more useful function to create. Don't worry too much about that. That's, well, do it. So the lab exercises for this week sort of do this sort of thing as well. They orient around creating strings and pulling and going from strings and on. So that sort of ties in a bit. That motivates why I've written the lab exercises like that. Malloc, yeah, on a general Linux, on my box here, if I ask for, maybe if I ask for a terabyte, everything's, but if I ask for a very large amount of memory, if I ask for 100 gigabytes, what Malloc will actually what the operating system will probably do is start killing other processors and try to give me the 100. So bad things may happen, but I'll probably get my 100 megabytes, but we can come back to that later in the course. This time for sure, you can make the caps lock. Oh.
There's also something called swap memory, which may, if you ask for way too much, may come into play as well.
Mm-hmm. Oh, yeah. Oh, see, I'd never think of that question. William's saying, could malloc allocate some memory but less than we asked for? Never thought of that, but no, it doesn't. Yeah, would be interesting. It would be an interesting memory interface. You ask for 4 terabytes and it says sorry, but here's 100 gigabytes. No, malloc, it's all or nothing. So it either gives you a pointer to what you ask or nothing. There's no bargaining. When will we learn assembly? Too soon. Next week's lectures we'll dive into assembly. All right. What's my next example? Hex string to int. Oh, reverse. All right. I meant to come back. So this whole function, yeah, SN printf can do the same thing. So there's a special version of printf that prints to a string. We're more interested in being able to do this ourselves. So this is about being able to do all of these things ourselves and understanding them. But if you're writing, if you needed this for a program, you'd actually go to something called SN printf, where the S stands for string and the N stands for bounded, I guess. But SN printf is it's a complicated function that we don't expose people to until we have to, but powerful, very powerful. Why do we want to know? Why do we want to understand assembly? Because it's there. No, more than that. Because we can't understand. We need to understand the real shape of a computer. It's crucial that we understand what's underlying, what the silicon does. It explains everything about what we see using computers. Now, all right. Let's go back to the next one. There we go. So this is a program. Let me compile it, run it, and then we'll see if we can see it work. It's hex string to int, and we'll put it in a file of a similar name. There we go. Guess I could have compiled it beforehand. So I can give it a string. So I can give it head, feed. That's a hex string. You see, you can make up any word you like with the first 6 letters of the alphabet. We can change. There we go. Bad. That's a That's a valid hexadecimal number. What is that as an integer? Do that in your head. B is 11, so it's 11 times 256 plus 10 times 16 plus D is 13, so that's 13. So you can do that arithmetic in your head. Oh, bad. Oh, once it's in capitals, does it? Bad. Let's try it like that. Bad hexadecimal is 2,999 base 10. There you go. All right. So my program here is not very flexible. It doesn't. Most things that accept hexadecimal will accept uppercase and lowercase. I'll leave it as an exercise. You can take my program and make it more flexible so it accepts both cases, upper and lower.
A fun fact is the word dead beef is almost universally used as a testing value because it can be written in hexadecimal.
Indeed it can and is, and its use dates to the early 1960s as a hexadecimal constant. There we go, and there it is, base 10. Apologies to the vegetarians out there who, well, I guess you're a vegetarian like me, you probably don't have to feel guilty about the dead beef. It's the meat.
The reason it's used is because it's 4 bytes, so it fits in an int, and it's very recognizable if you're debugging to see dead beef pop up.
DCC actually does that, by the way. It packs, if you malloc memory, it packs in a special constant. So if that constant pops up, it knows, oh, that's probably come from the student getting a value out of malloc memory without ever assigning to it. It doesn't use dead beef, though. It uses another one, I think. All right.
There's actually a Wikipedia page that catalogs all the different constants that are used by different systems. There's some interesting words that have been used for these debug values.
So that sounds a perfect thing. If you're fully vaccinated, actually, I guess many of you probably aren't fully vaccinated yet, and are having a legal picnic of 5 on the weekend, you can read up on that Wikipedia page on interesting hexadecimal constants used in testing and debugging, like dead beef, and that can be a topic of conversation. All right, don't say you don't learn anything useful in my course. Let's look at a problem. I've got a number 0 to 15, and I want to turn it into the corresponding... Oh, sorry, I lie. I don't have a number 0 to 15. I have an ASCII code such as 8 or C, and I want to turn it into the corresponding integer. ASCII code in, integer out. There really should be an assert here. What am I thinking, Andrew? There should be an assert there saying what the valid values are. So how do I do that? Well, we know that the ASCII codes for 0 to 9 are contiguous, so if it's in that range, we can get the integer just by subtracting the ASCII value for 0. If it's in the range A to F, we can get the value by subtracting capital A. And I guess we should have added a test there for little a to little f as well. Let me do that. Let me be a good... Fix my code. 3 if statements that are all pretty simpler. Should they be a function? Should I have one function called 3 times? You can consider that. Whoop. There, it now handles little a to little f. Quality coding. Alright. So we can now say dead in lowercase and get... There we go. Alright. So that's the hex digit bit. There must be more to this though. Right. There we go. I've got a string coming in, a whole pile of hex digits. I want to turn them into a value. So I've got DEAD coming in. I want to turn it into 57005. I've got 4 ASCII codes, the ASCII codes for D, E, A, D, and I want to turn them into 57005. I've got a function already that given one ASCII code turns it into 0 to 15. So ASCII code in, 0 to 15 out. What do I do then? And this is beautiful. I go through the string from start to finish, and this is another example of what Dylan talked about, how this encapsulates our loop in one line. It's information dense, which takes a while to get used to, but I like it. It's saying from which digit equals 0 each time around the loop, increment
Your
which
head's
digit.
blocking half of it.
Oh, that's bad. Wait a minute, I can fix that. It's back to the frog, but I'll turn off the frog. Alright, apologies for that. I'm so sorry that you didn't see the beautiful for loop. Starting at 0, incrementing, and we've got a different stopping condition. Our stopping condition is when indexing that array, that's not equal to 0. And that, then we have, you're always saying, Andrew, but you want to know that you're asking yourself, how do I know that that's a valid index? Well, I have to know that there's a 0 somewhere in that array. Do I know that? I really have to make that a calling rule. I have to put that back to the caller, saying something like hex string should be 0 terminated. So I have to push back to the caller. This has to be true. There has to. If I run through this array, I have to get to a 0 before I run off the end of the array. So I pull out the ASCII value. I convert that to a digit. That's all this code down here. And now I build up the value. I shift whatever I've got so far 4 bits across, and I put a new bottom 4 bits in place. Look at my master plan here. Or if I want to add bits to a value, I use OR. If I want to, so that anything that's a 1 in value and anything in 1 in this will now be 1s in the new value. Because I've shifted this across 4 positions, the bottom 4 bits are all 0s, so they'll get to be whatever the bottom 4 bits, whatever the 4 bits are of digit is in. So if an input is dead, I'll construct something that's got D, then DE, then DEA, then DAD. You're saying, is that really true, Andrew? Well, let me show you. I can debug that. I can put a printf here. I can use a %x to print out value, and I'm betting I'll see D, DE, DEA, DAD as we build up the value. You just watch me. I really should take notice of the syntax highlighting, shouldn't I? I'm not a taller syntax highlighting fan, but maybe I should be. Oh, actually, we don't want to be there. All right. Does this do what I say? Look at that. Printing out here, it's putting the value in, then shifting it across 4, putting it in, shifting it across 4, putting it in, shifting across 4. Let me show you the virtue of hexadecimal. Let's say I tried debugging in decimal. Still switch to getting base 10 information. Oh, recompile, Andrew. They're the same numbers, but I can't see what's happening because I can't do that. So it's really useful to be able to output and input in hexadecimal because each hexadecimal digit corresponds to 4 binary bits. We could also compile this program with print bits. That would be another thing you want to do if you want to try and understand that. So get the print bits function and stuff it in there. But again, this is what I'm talking about. You've got to understand this code. This code like this, if you want to work with bits and operations like this, you've got to understand this. This is core stuff. And the way to understand it is, maybe you read this and go, just from listening to Andrew and reading it for 5 minutes, I understand it. And that's wonderful. Far from everyone can do that. If you're not that person, get the code, add printfs, figure it out, read about these operations, put in some more things, try changing the code, and so on. Why 4? Yeah, it's a bit worrying, that magic number of 4 there. What are we doing? We're printing out hexadecimal digits. How many bits in a hexadecimal digit? 4. Okay. All right. And on. Oh. Let me try compiling this. I don't know if this program compiles. It's showing you things not to do.
Not with DCC, it shouldn't.
I'm not sure if DCC will compile it or.
It would definitely give a runtime error. Yeah.
It's going to give me a runtime error. This is harking back to my life advice. All right, so here we're doing I shifted by 1. I is an unsigned type, signed. It's a 16-bit signed type. This is undefined. Should it be? Yeah, it's an interesting question. The C standard slowly changing there, but not fast enough for you in COMP1521. So let's try running that. I think we'll get a runtime error from DCC. It'll stop at that line. Yeah, so DCC's saying you can't do that, Andrew. Which is not so scary. The trouble is there are computers out there which do different things for this. So you run your program on 2 different platforms, you might get different results. So that's bad. In general, the result is undefined. Oh, why -1? What I wanted there, by the way, was a value that was all 1s. And -1's an example of that. It's actually undefined for any negative value. So that's one problem. Shift of a negative value is undefined. Also undefined, left shift of a negative value. I can compile that and run it, I won't, but this is undefined. This one's more interesting. This is a positive value, but a left shift would make it negative. They're all pretty standard sort of things. This one's a bit weirder. I tried to show you this before. I'm going to show it to you again because it causes such a hassle for 1521 students. Well, coders generally. A lot of coders get confused at this error. Yeah, DCC's trying to warn. It could do better here. What's my trouble here?
I do enjoy how the only thing not underlined in that error message is the actual problem.
Trust me, if you dealt with some of the C compiler error messages I've dealt with in the past, you'd be leaping with joy at a message like that. C compiler error messages are not great, but they're not as bad as they used to be back.
They're improving.
Back when I was young. All right.
We have colors now. 2 years ago, we didn't even have colors.
I'm not unconvinced about the colors virtue, but all right. The trouble is a thing of types. If I write a number in a C program, when you're seeing there's 2 questions. There's what base it is. So 0x hexadecimal, starting with a 0 octal. Otherwise, it's base 10. So it's hex. It's octal if it starts with it's hex if it starts with 0x. It starts with 0, it's octal. Otherwise, it's decimal. And here's another fun fact for your picnic then. So you're having your COVID-safe picnic on the weekend, and you want to start a topical conversation. The constant 0 in a C program is octal, which is perhaps the most useless information you'll ever get in a university course. Because why is it useless? Because 0 is the same in all bases, so it doesn't really matter that it's octal. All right, so that's one thing, what the base is. So what base is this one? It's base 10. Doesn't matter a lot either, does it? Because 1's the same in every base as well. There's another thing though. What type is it? What types are really starting to matter? And it's type int. On this platform, int is the same as it's signed and 32 bits. It doesn't have to be, but it's a 32-bit signed number. And I'm shifting it here 33 positions. Now, what really confuses people is, oh look, but Andrew, over here I'm assigning it to J, and J, look, J is good. J is 64 bits unsigned. Why have I got a problem? The trouble is, the C compiler doesn't look at this bit here. It works out right-hand side first. It does all the right-hand side calculations and without looking at where it's going. Let me repeat this. C compiler doesn't look here. So it's not looking on at the left-hand side before it's done the calculation. You think it should? Perl's your programming language. But C compiler has a simpler semantics. We just calculate everything and then we do the assignment. So it doesn't know it's going into a 64-bit type. How do I get out of this bug? This is the complicated way. There's a couple of ways to do it. That's the complicated way. But let me show you the easy way. The easy way is just to put the 1 in a 64-bit variable and then shift that. But that's also the same. That's using a typecast.
The other way is the postfix notation 1 LU. Or
another topic for your picnic is, did you know if you put an LU after a constant in C, it turns it into an unsigned long constant?
Actually, I can't remember if it's LU or UL. It's one of the two. I can never remember.
I'd get that right. It'd be embarrassing at the picnic on the weekend if someone corrected you. All right, let's move along. Let's write my code and move along, because I have a fun program. Oh, that's a bit confusing. Let's look at the code and then run it. All right, what does this code do? It gets an int, an integer value from a command line argument. If it's less than 0 or greater than 255, it tells the user, try again. It then, here's a standard programming pattern. So this is what we know and love. That reads characters from standard in. Whoa, would this be better written as a for loop? Interesting question. Maybe not. I think this is probably better as a while loop, but you can argue about that at your COVID safe picnic on the weekend. It reads characters. Note we declare C as an int. Smart. Until we get EOF, and it puts them out after transforming them. So it reads from standard input, prints to standard output, transforming every character by XORing it with whatever value we put in. And XOR has this weird property that 0 XOR 0 is 0, 1 XOR 1 is 0, and otherwise it's 1. So let's compile my program, which I could have done beforehand, for XOR. And we'll XOR every value with 15. Hello, Andrew. Whoa! Okay, that wasn't good. It's changed the ASCII values of Hello Andrew by XORing them with... Uh-oh, and I've broken my terminal. How do I get that back? Well, that's not good.
Reset reset command. Even if you can't see it, should fix it.
No.
Or there's the magic sysrec key. What sysrec is it?
I'm not going to type sysrec commands right now. I think that would be bad.
There's a sysrec text mode, but I can't remember which key it is.
So we've got interesting character code come out, and my terminals apparently do interesting things with those character codes. So bear with me. I'll show you how to look at this safely, if I can. There we go. Let's stop that. Oh! Alright, and I'm an idiot. It was just still stuck in. Alright. Let's just send the string Andrew into the program, and we'll XOR it with 25. Becomes this fairly random sequence. Echo just puts Andrew just about. But what if I put this through XOR again? So I XOR every value twice. Don't worry too much about what we're doing. XOR has this amazing property. If you get a value and XOR it with, you get X XOR Y, you get seemingly random thing. If you XOR it with Y again, you get your value back. So that will get Andrew back. So XOR gives you this transformation to seemingly random bit string, and then you can transform back. Why is that interesting? It gets used a lot in cryptography. Now you're saying, all right, you can't do cryptography in this. You've transformed Andrew to some weird thing, but it's dead easy to transform it back. No, that's not how it works. In cryptography, they construct cryptographically the string you're XORing. So you've got text you want to encrypt. They'll XOR it with well. I'm quickly getting into my depths of cryptography. You can do. The maths department has some nice cryptography courses, I think. You can do cryptography there and know much more about that, mate. But XOR gets used at a low level in cryptography to high things. You also do nice things in graphics with it. So I can try that again. If I XOR, say, with 42, type in. Let's type in sensible characters. Color XOR. I get weird things back. If I stop the program, but if I send XOR 42 also into XOR 42 and type in hello XOR, it will be XOR through and then through again. Try this yourself. You can just write little programs that do, value XOR and then XOR it again and do with printfs. But it's this weird property. Yeah, XOR is its own inverse. Yeah. It's a weird and nice property. It's fun.
You shouldn't break your terminal unless you put in a number greater than 128, because that will then flip the first bit, and when you flip the first bit of an ASCII value, weird things start happening.
Another trick would be to pipe at the cat -a's, which turns weird values into OK values. And it's fine with us. All right. All right. We're running out of time here, but I'm going to use my last few minutes to show you a nice way to use bit operations to store a set of possible values. And we're going to hark back to something you did. Some of you have done as a 1511 assignment. Let's suppose I have a set of possible values. I've got 16 possible values there that I want to store as a set. So I'm going to have objects, Pokemon, that can have any subset of these 16 values. They might be dragon type, ice type, and psychic type. So they can have any subset of these 16 values. You're saying, well, I can do that, Andrew. I'll have a array of 16 values which are true if it's got fire type, and false if it doesn't have fire type. True if it's got fighting. So I'll have an array of 16 types, and that's fine. So you might declare, an int 16 array like that, maybe, to do it. And that would be perfectly normal. That would be, we'd be smiling if you're coming out of 151 and you're doing that to store these values. But you can actually do it if you wanted to save space, if you needed to save every last little bit of space. Pity Jashank's not here for the pun, but if you could actually pack all of these into a single 16-bit value. How do we do that? Like this. So we set this bit. Well, what do you notice about my hexadecimal constants here first? I've written them in hexadecimal. Each of those hexadecimal constants, if you write them out in binary, just has a single 1 in them. So this last one is 1 followed by 15 zeros. This first one is 15 zeros followed by a 1. So they're all a 16, they're all got just one of the 16 bits set, I'd say. Just there's only a single 1 and the rest of the number is zeros. And as we come down here, the least significant bit is 1, second least, third least, until we get here. The top of the 16 bits is 1. So we've specified we're going to, if a Pokemon is bug type, that this value should be 1. How do we make use of that? All right. Oh, by the way, you're saying, Andrew, this seems silly, and I don't like Pokemon. Maybe you love Pokemon. This is exactly how a lot of device drivers work. Interaction with hardware often happens exactly like this. So this is a very real way of coding, even if you don't love Pokemon.
If you ever have, or in future will do, Arduino programming, you always have hash defines for each pin. You'll always have this pin is a certain thing, this pin is a certain thing, and it's always in a lovely list of hash defines.
So if I want to create my Pokemon and represent its types, I can use OR to do that. I can say, if my Pokemon is bug, poison, and fairy, I say it's bug type, or poison type, or fairy type. That will OR those three values, and I'll get a value with 3-bit set. I can then print it out, and then tell which types it is. Let's go down to the. I hope we can run this. Let's try. Is it Pokemon.c? Yes, it is. Let's compile Pokemon.c. We're getting close to the hour. I know. I apologise. You may have to save questions for tomorrow. And we run Pokemon. All right. This is what I was talking about. So this is what we're talking about. Oh, I have to come down a bit. So bug type is here. Look at it as zeros and ones. That's what it is, zeros and ones. Poison type is there. That's it, as zeros and ones. And fairy type is here, and that's it, as zeros and ones. I've said my Pokemon is bug, poison, and fairy, ORed them all together, and I get a value that's got ones in the appropriate place. How do you use that? And sorry. Sorry, I keep typing the wrong sequence. There we go. All right. To wrap this up, if I want to know, if I've got a Pokemon and I want to know if it's poison type, then I can AND it with poison type, and it'll say that value will be true. If I want to know it's ghost type, I can AND it and that, and we can see that works. It prints out poisonous, but not scary. If I want to add a type to it, I can OR equal with it. Oh, and here's a nice one. Yeah. So you can read through all of this at your leisure. If I want to remove a type, how do I do it? I get the type. That's just got 1 bit set for that type. I negate that, and I get a value that's now got a 0 for that, whatever that type has the 1 bit set, and 1s everywhere else, and I AND it. So that's an important operation. That removes the person, that bit. And you can see here we removed that 1 bit and took it out there. All right, sorry,
You can also do the same thing with exclusive OR.
Yes, you could. All right, and as Dylan said, this is a Pokemon example, but lots of real-world, low-level hardware programming looks exactly like this. So Dylan mentioned programming in Arduino. We're out of time. I won't answer any questions we've got now, but save your questions up. We'll look at one more example like this before we launch into floating point numbers next week. All right. Thank you all for tuning in today. Sorry, next week, tomorrow. I'll talk to you all tomorrow. See you then. Enjoy diving into the course material. There's a lot in this week's lab. But it's not too hard. It's interesting programming. There's a lot to learn there, a lot to practice. You'll have great fun. And your tutors will help you out. But you can get started on that. All right. Thank you all for that. Let me